Unit 7, Day 7, Rational Functions Not in Graphing Form. This is Mr. McGough up in R12. I'm going to go over these notes with you. So first off, a review from prior lesson. So we're trying to figure out which of these four functions, A, B, C, or D, describes the graph to the left. So some things we can see. We see that we have a vertical asymptote to the left of the y-axis at x equals -3. We also see that we have a horizontal asymptote at 1, 2, 3, 4 above the x-axis, so that's at y equals 4. The other thing that we see is we recognize that the standard, or the parent function 1 over x, is flipped compared to this. So that means that our function itself will have a negative sign out front. So what we're looking for, horizontal asymptote, is y equals 4, so that's k. So we see that that's true on all four of our potential options. We see that our vertical asymptote is -3. Well, we remember, though, that this is actually 1 over x minus h plus k, so minus h. So if it's at -3, it would be x minus -3, which becomes x plus 3. That's true on A and B. And then we recognize that flip or reflection across the x-axis. So our answer is A. What is the maximum number of horizontal asymptotes a rational function can have? Well, a rational function can have 0. We're used to those functions. We can have 1, like we do here, or you can actually have a function that looks kind of like a letter S, and it would have 2 horizontal asymptotes. That is the most that you can have for a rational function. Moving on with our notes. First, the steps to graph rational functions. First, you're going to factor them and cancel out repeated factors. So if, for example, you had x over x times x minus 2, you'd be able to take out x over x. And you'd be left with 1 over x minus 2. From there, you're going to then find the vertical asymptotes. So those numbers that make the portion with x equal to 0. Then you're going to find your horizontal asymptotes. Then you're going to find your x-intercepts. How do we find x-intercepts? Well, we know that for an x-intercept, y is equal to 0. So we're going to set our function equal to 0. You're then going to put your function into graphing form and use a table and symmetry to find the points near those vertical asymptotes and plot that. And then you can use your graphing calculator to check your work. Holes. What are holes? Well, holes occur when you have the same factor. So when factors are the same in the numerator as in the denominator. That's a lot of words. You could also say holes exist when factors are able to be removed. So the example I gave up above, x over x, it has the same factor in the numerator and the denominator, and I can factor out x over x, which is equal to 1. But I also need to recognize that if x was 0, that would cause this to be undefined. So that would be a removable discontinuity, which is called a hole. A vertical asymptote. To find that, we're going to set the denominator equal to 0 and solve. So really, again, like in our example, we see that x minus 2 would be what was left of our denominator. So if we set x minus 2 equal to 0, x equals 2, that would be our vertical asymptote for that little example. Horizontal asymptotes. Here we're looking at f of x, which is a function which has a polynomial with degree n on top and a polynomial with degree m on the bottom. So numerator has an n, denominator degree m. So this is a rational function. It's a ratio of two functions. And the power on top, in this example, case 1, the power on top is less. If that happens, we'll have a horizontal asymptote at y equals 0. If n is greater than m, we'll jump to case 3. Well, think about it. You have x to the 4th divided by x to the 3rd. Oh, by the way, this one would be like x to the 3rd divided by x to the 4th. You could reduce that to 1 over x, which would be our 0 for an asymptote. If our power on top is bigger, this would reduce to x over 1. There would be no horizontal asymptotes. And then what if it's the same on the top as it is on the bottom? Well, there we're going to have a horizontal asymptote which is equal to the ratio of the leading coefficients. So for example, if I end up, and when I reduce, I factor out common factors from the numerator and denominator, and I end up with something like 2x over x, or 1x I should say. Here we would have a horizontal asymptote at 2. So it's the ratio of the leading coefficients. X-intercepts. Define the x-intercepts. By the way, x-intercepts are an x value and then y equals 0. So it is where a function crosses the x-axis and it crosses the x-axis where y equals 0. So to find the x-intercepts, we set the equation, the y value, the output, equal to 0 and solve. Graphing form. To put a function into graphing form, we're going to use long division. To rewrite it. And remember, in yesterday's notes, we went over the fact that the form that we want to end up with is 1 over x minus h plus k. Well, really a over x minus h plus k. So when we do our long division, k is going to be really, when we do our long division, that'll be up front, and then a over x minus h will be our remainder. Finding vertical asymptotes for each rational function. Here we're going to look right back at those three cases. In example number 1, x to the 0 power on top, x to the first power on the bottom. So, n is less than m, case 1. We get a vertical asymptote at x equals 0. That's this part. And that's our vertical asymptote, and a horizontal asymptote is what we use up above. And we get y equals 0, because n is less than m. So again, vertical asymptote, we set our factor in our denominator equal to 0, so x equals 0. And for our horizontal asymptote, we compare the power of the function in the numerator to the denominator, and in this case, the numerator power is less than the denominator, so y equals 0. On problem number 2, our vertical asymptote will be 8, x equals 8. And our horizontal asymptote, I have n over m equals 1 over 1. So we'll be at y equals 1. On problem number 3, I have an x squared term on the top. I have an x term on the bottom. Let's work with the bottom first. going to set 2x plus 1 equal to 0. So we will have a vertical asymptote at x equals negative 1/2. Our horizontal asymptote, well, we have n, which is squared, and we have m, which is a power of 1. So n is greater than m. We look back at our table. If n is greater than m, there is no horizontal asymptote. On problem number 4, vertical asymptote. I'm going to set x equal to 0. Horizontal asymptote. Well, here, the first part, n is less than m. That would give us a vertical asymptote at 0. Excuse me, horizontal asymptote at 0. But we now have plus 4. So we're going to add that 4, and we're going to get y equals 4 for our horizontal asymptote. So we get this part, gives us y equals 0, but then we still have plus some k at the end. Problem number 5. Our vertical asymptote. We're going to set 2x squared plus 1 equal to 0. Subtract 1 from each side. 2x squared equals negative 1. Divide both sides by 2. X squared equals negative 1/2. If I now take the square root of each side, what I'll see is this is a square root of a negative number. That's imaginary. So this will have no vertical asymptotes. Horizontal asymptote, though. We take a look at our coefficient. Well, first off, we recognize that n equals m, so we look back at our table. If n equals m, our horizontal asymptote will be the ratio of the leading coefficients. So our leading coefficient on the top is negative 1 for the x squared term. Our leading coefficient on the bottom, which by the way, that's not in standard form, it should be negative x squared plus 4. Our leading coefficient on the bottom, on the denominator, is 2. So we get a horizontal asymptote at y equals negative 1/2. Find the holes, asymptotes, and x-intercepts for each rational function. So first, we're going to see if these can be factored. Here, x squared plus 9 is x plus 3 times x minus 3. Our denominator, x squared minus 7x plus 12, is x minus 4 times x minus 3. Here we see we have the same factor, x minus 3, on both the top and the bottom. So that can be factored out. However, when we factor it out, we know that when x minus 3 equals 0, this would be undefined. So we have a hole at x equals 3. Now we have x plus 3 divided by x minus 4. So we're going to look at our vertical asymptote. First thing we're going to do is we're going to set x minus 4 equal to 0, and that will give us x equals 4. We can also take a look, since we've factored out x minus 3, we have x plus 3 over x minus 4. There we have n equals m, first power over first power. We'll look back at our table. When n equals m, it's the ratio of the leading coefficients. Our ratio of our leading coefficients, it's 1x to the first over 1x to the first. So we have a horizontal asymptote at y equals 1. Go ahead and pause your video and try number 6 on your own. Pay attention to the fact that the first thing you're going to need to do is factor. Okay, so when we go to factor this, first we'll take out a greatest common factor of -3 on our top, and we have x squared minus 2. X. So really, I should have taken out -3x. So we'll take that out. And we're left with x minus 2. On the bottom, we have x squared minus 16, which is x plus 4, times x minus 4, and then we have x minus 2. So we look for this common factor, x minus 2 over x minus 2. We will remove that. That's equal to 1, but it is undefined at x equals 2, so that is a whole. Now we're going to look at our vertical asymptote, when we're going to set our denominator equal to 0. Well, we have two options here. We can set x plus 4 equal to 0, and we can set x minus 4 equal to 0. Therefore, we have two vertical asymptotes, one at x equals -4, and a second at x equals +4. Horizontal asymptote, we're going to set the whole function. We're going to take a look at our powers. So I have x to the first power on top, and x squared on the bottom. Taking a look back at our table, we see that n is less than m. Therefore, our vertical asymptote is at y equals 0. Graphing rational functions. Number 7. So the first thing I need to do is get this into graphing form. So that's going to require me to do some long division. So I'm going to go x minus 1 goes into x plus 4. I look at x goes into x once. I'm now going to subtract this from my original x plus 4. So x minus x goes away. 4 plus 1 is 5. X can't go into 5, so I have a remainder. So I get 1 plus 5 over x minus 1. Really, in standard form, I take the plus 1 and put it at the end. That's my k. So I end up with 5 over x minus 1 plus 1. That's my new y in graphing form. So do I have any holes? No. No common factors top and bottom of my ratio. Vertical asymptote. Vertical asymptote, I set my denominator equal to 0, so I have a vertical asymptote at x equals 1. So, horizontal asymptote. Well, let's go back and take a look again at this. First, we're going to take a look at the fraction, 5 over x minus 1. So here I have n equals 0, m equals 1, n is less than m, so that's 0. But then I have plus 1, so I'm going to add 1 at the end. So my horizontal asymptote is at y equals 1. X-intercept. To get the x-intercept, I'm going to set y equal to 0, because this will be something comma 0 for a point. So 0 equals 5 over x minus 1 plus 1. Subtract 1 from each side. 5 over x minus 1 equals -1. I'm going to multiply both sides times this denominator, x minus 1. So x minus 1 times -1 becomes -x plus 1. 5 over x minus 1 times x minus 1 gets rid of the fraction. We end up with 5. Subtract 1 from each side. Negative x equals positive 4. So positive x equals negative 4. So our x-intercept is at negative 4, 0. End behavior. Well, let's graph it to figure out our end behavior. So I'm going to set a vertical asymptote at x equals 1. We're going to set a horizontal asymptote at y equals 1. We're going to have an intercept, an x-intercept at negative 4, 1, 2, 3, 4, 0. So what if x equals 0? What do we end up with? Well, we get 5 over negative 1, which is negative 5, plus 1. So that's negative 4. So we'll plot point 0, negative 4. And what we can see is we have a couple of points. If we want to add a couple of more, we could say, for example, x equals negative 1. So 5 over negative 2 is negative 5 halves, plus 1 is negative 3 halves, etc. Do as many points as you feel is necessary to get your graph looking symmetrical. Now we'll go ahead and connect our dots. We're going to have its reflection on the other side. So up 1, 2, 3, 4. And a couple other points. Remember, this is symmetrical, so we think about it as symmetrical across the intersection of the horizontal and the vertical asymptotes. So we'll have something like, let's see, if x equaled positive 2, we'd have 5 over 1, which is 5, plus 1 is 6. So here's the point 2, 1, 2, 3, 4, 5, 6. If x equaled, say, 6, we would have 5 over 6 minus 1, so 5 over 5, which is 1, plus 1 is 2. So we'd have the point 6, 1, 2, 3, 4, 5, 6, 2. And then we would have our curve going between them. And we can look at our end state behavior. I'm going to go ahead and write it off to the side here. Our end state behavior will be as x approaches negative infinity, y approaches positive 1. As x approaches positive infinity, y approaches 1. As x approaches 1 from the left, y approaches negative infinity. And the last one, as x approaches 1 from the right, y approaches positive infinity. Using that process, go ahead and try number 8 on your own. I'm going to go ahead and pause my video. You do the same, and then I'm going to fill everything in and restart it so you can check your work. So hopefully you took the time to go ahead and go through this problem on your own. So the first thing we're going to do is we're going to factor this problem. So 2x squared can be factored into 2x times x. The x over x is a removable whole. So we have a removable whole at x equals 0, which on my graph I should draw as a whole. Next, we want to get it into graphing form, so we do our long division. X plus 2, well, first we get rid of that x over x, that's a removable whole. So we end up with 2x divided by x plus 2. So x plus 2 goes into 2x twice, with a remainder of negative 4. So we have negative 4 over x plus 2 plus 2. Our vertical asymptote, x plus 2 we set equal to 0, so x equals negative 2. We'll plot our vertical asymptote at x equals negative 2. Horizontal asymptote, we take a look. I have 2x over x plus 2, so they both have the same power. Or I can look down below here, and what I get is 2 over 1 for my horizontal asymptote. So I plot my horizontal asymptote at y equals 2. Now I want to calculate my x-intercept. So I take my rewritten function, I set it equal to 0 and solve. 0 equals negative 4 over x plus 2, quantity plus 2. Subtract 2 from each side. Multiply each side by x plus 2, so I get negative 2x minus 4 equals negative 4. Add 4 to each side, divide by negative 2. X equals 0 is my x-intercept. It just happens to be that that's also where there's a hole, so I draw a hole around my x-intercept. End behavior, as we see here, as x approaches negative infinity, y approaches 2. As x approaches positive infinity, y approaches 2. And then as we go towards that vertical asymptote, as x approaches negative 2 from the left, y approaches positive infinity. As x approaches negative 2 from the right, y approaches negative infinity. So I look forward to seeing you in class and going over some more of these and getting you ready to do your homework. Have a good day.